Morning, everybody. So I am going to take us through a bit of a tour of earth science in Tongariro National Park, the geology, volcanology, and hazards, from kind of the perspective I take anyway. And I'm also going to weave in an update on recent eruptions. The two most recent eruptions we've had to deal with are Tamari from Tongariro in 2012, but then also Whakaari, the tragic eruption in December last year, which caused the fatality of at least 21 people at White Island Whakaari offshore. So I'll talk that through a little bit at the end. I guess you want to hold questions till the end, Susanna? Is that the structure for you guys? Probably the easiest.
Yes, sorry. So as usual, people, if you want to ask a question, you think of something, put it in the chat. Otherwise, okay, we'll hold them for the end. Yeah. Great.
So I'll try to get through in about 35 minutes, and then so about 40 past, we'll go into some questions. That's about the timing you want, Susanna? Cool.
Yeah.
Okay, so now let's see if I can advance my slides. There we go. Okay, so as Susanna said, I'm a senior volcanologist here at GNS Science. It's basically the New Zealand Geological Survey, but we also do warning for tsunami. So we're pretty much like USGS plus tsunami. I've got a PhD in geology out of University of Canterbury, and I worked on volcanic eruption histories basically for that. But ever since then, I've had quite a multidisciplinary career path, as Susanna talked about. And in fact, I believe this masked figure in Vanuatu from a couple of years ago is Susanna, and some of that ruthlessly efficient field work. And the key to the work I do, I basically work on volcano maps, both eruptive history and hazard maps, but I also work in warning, and in that I've been involved with our tsunami evacuation mapping framework and tsunami warnings for the 15 years I've been here as well. And the maps are really the key for me. So all the photos there relate to maps. One of the nice things about being in a multidisciplinary position is you get to do a variety of different things. So this is drilling ash cores, one of the lakes in Auckland for the eruption history there. And a real highlight in the last few years is I got to coordinate the science input to our upgrade of our new national museum Te Papa exhibit on volcanoes and other earth science. Can you see my cursor when I move it, Susanna? Or do I?
Yes. Yes.
You can. Okay, cool. Right. I don't need to use it. Right. So I'm going to talk about Ruapehu and Tongariro volcanoes, our approach to mapping, and the different techniques you can see there in the bullet points, and ultimately how it led to quite a major reinterpretation of those mountains' evolution. And I'll touch on the implications for hazards and warnings, which I also work on. And I'll finish with a bit of a summary of that deadly Whakaari eruption and our communications around that, and that kind of the hazard communication aspects at the end. Okay, so Ruapehu and Tongariro are both stratovolcanoes. So they're these multi-layer, build up over time over one or a few vents, classic volcanoes. At primary school, you'd be asked to draw a volcano, you'd draw a stratovolcano. And they tend to fall apart through collapses and under rain, kind of lahars, mass erosion. In New Zealand, we also have other types of volcano. We've got scoria cones, little scoria cones like this in Auckland. That's what Auckland's volcanic field is. We have rhyolite volcanoes where we get explosive eruptions and often form lava domes. And every now and then we actually get these caldera, every few tens of thousands of years, get these huge caldera forming events where the eruption is massive across the southern hemisphere. You erupt and lay out a big ignimbrite of ash, an ash sheet that forms ignimbrite, and ultimately in a big sinkhole, you collapse the ground and leave a depression, and that's what Lake Taupo and some of our lakes are. But today we're talking about cone volcanoes, so we're not talking about those. We are talking about these. We're talking about stratovolcanoes, just to avoid that confusion. So to show you where those are, there are some fields of these little scoria cones, like I show you from Auckland here in Auckland and to the north. You've got a caldera complex right here in the middle of the North Island, and that's where you've got this Taupo caldera, Rotorua and Okataina calderas, and a bunch of others. But I'm talking about stratovolcanoes. So Whakaari offshore is a stratovolcano. It's just the tip of it is poking out of the water. Ruapehu and Tongariro are stratovolcanoes. Taranaki is kind of this stratovolcano with a stack of domes that we were talking about before the lecture. And And all of these, other than Auckland, are on an arc of volcanoes that stretches all the way from Taupo to Tonga offshore. So it's an arc, part of the Ring of Fire, stretching offshore. So I'm just talking about the very southernmost tip of that, Ruapehu and Tongariro. They're the first volcanoes on the arc all the way up to Tonga. Okay, so we published a map in 2017, a geological map, and a 100-page book describing the eruption history at Tongariro National Park. And I'm going to be talking through the research that went into that book and bulletin that we published. And you can buy that off our website if you are inclined. So Dougal Townsend is the other main geologist I've worked with on this. That's him, back of his head on the left and the back of my head on the right. And we worked on the regional mapping of New Zealand back from 2000 to 2010. And we did a bit of preliminary work in Tongariro National Park and realized there was no detailed published geological map of the park. And we were suspicious of the eruption history being described. There's a strong overlapping volcanic and glacial history there. And we were wondering if there's evidence of that interaction. So we dived into a big mapping program with several PhD students. And I'm just going to talk through the way we went about this. So one of the key things we do these days is detailed on-screen compilation digitizing. So we've got high resolution air photos and elevation models. And Dougal's a great geomorphologist. So you can see here, for example, this is in the Whakapapa ski area. There's a building right there. And you can see him drawing boundaries on different polygons that he can see in 3D from the stereo air photos. We also, from those photos, because they overlap, we can get the computer to build us a terrain model from those photos. Now, the gold standard here is to get LiDAR, laser-based elevation data, but we don't have full coverage for the park yet. So we use this technique. And this is what old-fashioned topo maps look like. And this is in the northern part of the park in a place called Tamari. This is a crater. And this is what an elevation model from air photo interpolation looks like. And it's not very different to LiDAR, actually. You can see all the little crenulations in the lava flows. You can even see the benched cut from the Tongariro Alpine crossing track in the images for that. We use a lot of microscopic lab techniques, and we partner heavily with Victoria University for this, and Leo Pure and Chris Conway under Colin Wilson's supervision, and John Gamble and Bruce Charlier have helped out a lot there. And then also from an argon dating point of view, we collaborate closely with US Geological Survey and Andy Calvert at Menlo Park. So I'll talk about those next. So the fieldwork component involves linking what we're seeing in the field with what we're generating on those maps and collecting a lot of samples. So this is what the countryside kind of looks there on a crappy and a good day. We spend a lot of time with topo maps, drawing geomorphological boundaries and checking the ones and editing the ones we've developed from a computer. It's Dougal and me doing a bit of that in the field. And we take a lot of rock samples with our students. So it's classic andesite lava. It's intermediate lava, and this is what chunks of it look like. I'll talk through argon dating first. So to find out when the different lavas were erupted from these volcanoes and piece together their life history, we need to get absolute age dates, and we use the argon-argon method of the potassium-40 to argon-40 decay. So we'll cut thin sections of rocks and take them back. And if they've got a nice texture, we're looking for fine crystals in the fine ground mass here to do argon dating. We'll then crush the rocks if they look good in a thin section, and take the crushed rocks and we'll run them through a magnetic separator. We want to get rid of the magma chamber crystals because there's no potassium in those, and just get that fine ground mass around the crystals and that crushed up material. We clean it up, and then I send it off to the US, and we throw it into a nuclear reactor. USGS use a 10-meter high trigger reactor, and this allows them to bombard it with neutrons and knock off a monitored amount of the potassium-40 to argon-39. So we can then precisely measure argon-40 and argon-39 in the same mass spectrometer. So it's basically potassium-argon decay, but much more precise thanks to this nuclear reactor. And that's it naturally glowing blue because of its radioactivity. I then fly over and I load the radioactive samples into the mass spectrometer. And this is the setup we use. So you're basically measuring different isotopes of argon windowless room for a couple of weeks every year, but the data is great. As well as argon, we also use paleomagnetism. So these are students working on Tongariro National Park, drilling cores out of lava, and they work out what orientation the little core of lava was before they pull it out, and they mark it, and then they put it in a machine and measure the magnetic field in it. And it tells them, they can compare that to a record of the orientation of Earth's magnetic field that we've got for New Zealand in the past. And so they can work out roughly sometimes where in the past that sample was from, just based on where the magnetic field was when the rock cooled and locked the signature in. The argon dates I just showed you also help improve the record of understanding New Zealand's magnetic field. So there's kind of a to and fro with that. We bring these two dating techniques together, that's argon dating and paleomag, and also our field mapping, to get a feel for the progression of ages at Tongariro and Ruapehu. So you can see here, these are results that Leo's brought together for Tongariro, and you can immediately see there's clusters of more dates during various parts back in time. So these are in thousands of years. So we're looking at a record from about 300,000 years through to present. And you can see the two stratovolcanoes have had bursts of activity that at slightly different times, which becomes interesting. So then we look more closely at that time record and start to think, okay, well, when has there been ice on this volcano? Well, it turns out there are a lot of moraines on this volcano. So this map just shows in green the moraines. These are ridges of bouldery material pushed by glaciers. And that was the first thing that got us interested in how much ice played a part. The yellow bits are all the washed out stuff that's come off glaciers. This is Sean Eves, another one of our PhDs, and he worked specifically on dating these moraines and modeling where the ice might have got to in the past. He used helium isotopes and cosmogenic dating to look at how long these boulders had been sitting out receiving cosmic rays, and got calculated ages for the moraines. And then we brought that back and integrated it with the lava ages, and we can see how the ice ages, so those are marked in blue for the past 250,000 years here, compared to when the volcanoes have been active. And so we can start to piece together where the ice is and where the lava is over time. You can see the volcano has been pretty productive during both ice ages and the Holocene and the penultimate interglacial. The other thing we do is look in the field for evidence of how those lavas might have interacted with glaciers. And turns out there's some really interesting textures there. Now, Sporley was a publication about 30 years ago that noted in one part of Ruapehu there were very fine lateral columns, and these were probably linked to ice. And so we had a look at that and we thought, oh, well, that's really interesting. And we started seeing them everywhere. And we thought we must be missing things. So Dougal and I arranged a week at Mount Rainier in the Cascades with Tom Sisson from USGS, because he'd interpreted this there. And we wanted to look at the evidence at one of the few other volcanoes where there'd been a lot of documentation of ice interaction. And it looked exactly the same. So we looked around there. And a key thing with lavas is when you get columnar joints, they point towards the surface that they cooled against. So normally lava that's cooled in the atmosphere, the columnar joints point upwards, and they're quite big because they've cooled slowly and they're pointing to atmosphere. If you get really fine ones that are about this big and they're pointing out sideways, they've cooled very quickly against something beside them, and that's ice, basically. They don't tend to stick around because they're delicate. So you find them in a few places. In this case, we see them, that's a very lucky outcrop. But they're kind of the smoking gun for lava interacting with ice. Then there's the landscape size signatures. So this massive 100-meter high colonnade of lava is way too thick. And then if you get up close to it, there's one or two little places where these lateral columns exist. And it's basically a place where ice has been sitting there, lava's flowed up against it, and it's been buttressed and over-thickened in against ice. And there's a lot of places like this on Ruapehu. In the valley walls all over both volcanoes, we see places where there are thick stacked lavas, and every now and then we see again those lateral columns just in the odd outcrop, indicating that it's not a case of this having been a cone volcano where the glaciers have cut into the valleys, but rather these valleys were full of ice, and the lavas have come down next to the ice, and they have not been able to get into the valley. And this is a key point about volcano-ice interactions that's emerging internationally. When you've got a valley full of ice, the lava can't easily get into it, and it actually stacks up next to the ice. The ice is not actually particularly erosive on good solid lava. You can see another place here. Again, these thick bits of lava poking through. But in the case of this valley, you've also got these thin lava flows that have got down right into the valley bottom. So this spot, you can see this edge right here. This is a thin lava that's come in the last 10,000 years after the ice retreated and made its way down into the valley because the ice is gone. So we can see that interplay. Then when you look back at the argon dating, you realize that it makes sense. The argon dates on these thick lavas that form the valley wall, they're all in the Ice Age. And the argon dates on the thin lavas that flow down into the valley bottoms, they're in the Holocene. We're back in the penultimate interglacial, back before the last Ice Age. There's some even cooler textures. We find these subglacial flows where lava has managed to get into meltwater tubes in the glacier, and you actually have columns pointing in every direction, even upwards, really little columns. And the lava's frozen in a meltwater tube inside the glacier, and then the glacier has melted away and left these kind of hedgehogs of lava columns behind. And they see these a few times at Rainier, and they're all over the place at Ruapehu. We just hadn't realized what they were before. This is the best image of one of those. We found kind of late in the piece in the Tongariro Valley. There's a person there for scale, about that big. So the field of view here is over 100 meters high. And what you've got here is a bunch of till, a bunch of moraine that was under and beside the glacier, a bunch of lava, this is the valley, a bunch of lava that's stacked up against the glacier. And then right here, a bit of lava managed to sneak into a meltwater tube and freeze inside that meltwater tube. And this knob of lava is completely surrounded by these very fine radiating columns that came from touching the ice. And then the ice melted away.
I mean, you are muted. We can't hear you.
Yeah. You muted yourself somehow, or it's muted. There
How
you
did
go.
that happen? Maybe someone else did it.
I hope it wasn't us. Sorry.
Yeah.
So we got to where you had the. Right? Yeah. So it was where you were talking about the knob of lava that had all the. That got into the meltwater. Yeah.
Right. So the other type of evidence we see of interaction with ice is Hyaloclastite breccias, and these are things you normally see underwater. So you see them in submarine, you see them in the Mediterranean from stuff that's been lifted out of the water that was erupted underwater. And they're basically pillow lavas in a breccia, very fine clays and ash. And we interpret them as being, Ruapehu and Tongariro, places where eruptions have occurred under ice, melted the ice a little bit, and they're basically then erupting into water. And they're huge. They're right in the core of Ruapehu, up the Tongariro Valley and other valleys. Got another photo. They look like this. That's my boot, and you can see these pillow lavas and these fine brecciated material around them. It's quite classic Hyaloclastite textures. And then on Tongariro as well. One of the highest places on Tongariro, if you've ever done the Tongariro crossing, and a bunch of you would have, it kind of comes up over here off to the left. And if you go over to the peak of Tongariro, there's lake sediments and jointed lavas and little blobs of pillow lavas on the top of a mountain. And it's because those were actually erupted under an ice cap on top of Tongariro, inside water, and that ice has now melted away. So to synthesize that ice record, Chris Conway's, for example, at Ruapehu brought this together. All the blue lines are the extents of ice and where the lavas come into contact with ice. It allows us to tell how thick the ice is and when it was there. And ultimately, the answer is Ruapehu and Tongariro were never simple cones. So there's a picture of Ruapehu. It's always been this ugly, hackly, rough-looking beast. It's what you get when magma and ice spend 95% of their lives fighting with each other. And actually, the last 10,000 years are the anomaly, when all the ice has retreated and left behind this almost Icelandic, well, it is a typically Icelandic stack of volcanics. It's just the ice record's gone. So here's one of these wedges of lava, and this is where the big glacier would have been in all of those cases, down this valley here as well. So I've talked about argon, I've talked about paleomag, I've talked about the textures from lava and ice, and magma and ice. I've talked about the field mapping. The last main technique that comes together to get the eruption history lined up is geochemistry. So this is the lab at Victoria University, and we use precise trace element chemistry and mass spectrometers to get our fingerprinting on the lavas. So if we can get ages for the odd lava, and we can map where they are, if we take a lot of samples of the lava, we can work out which ones are the same. So these color codings are just based on chemistry. You can see all these lavas are basically the same. And so when we're making a map and fitting a piece of the map into the history of the volcano, we lump these guys together, and we have a date for it. We know it's only 5,000 to 7,000 years old. Whereas this ridge has lots of different chemistries in it, but one dominant chemistry, and that's 170,000 years old. This is a ridge from the penultimate glaciation, not the last one, but the one before. And this valley has been occupied by massive glaciers twice. And then it's been filled in by lava just in the last few thousand years. And we really are able to piece that together using all the techniques, including chemistry. We spend a lot of time using ArcMap's multivariate live geochemistry. So you can plot data in many domains from a map in ArcMap. So I'm just showing this because there are a bunch of environmental and earth scientists on the line. The ability to plot intensive data in bivariate plots against maps is a really powerful thing that not many people know about in ArcMap. It lets us go back and forth between views like this, and we can actually select individual points, and they will be highlighted on a geochemical plot, and we can look for clusters like those purple clusters in a geochemical plot, draw a box around them, and they'll turn up on the map, and we can find out where they are. So you can use that for any type of environmental chemistry or data. It doesn't have to be rock geochemistry. We bring it all together. Now, again, coming back to GIS, we now do a lot of live visualization, especially in Arc Pro, where we can take a 3D model and drape it with air photo or satellite imagery like this, and also drape it with our draft geology and try and test whether in 3D our model of these Holocene lava flows getting into valleys that were otherwise full of ice makes sense from 3D. And ultimately, we can bring it back and answer some really cool three-dimensional questions, not just how the volcano built relative to ice, but we've kind of been able to more definitively solve one of the outstanding questions around a big collapse at Ruapehu. There's a place called the Mounds on the drive up to Whakapapa village, which is over here. And it's a bunch of mounds from the collapse of Ruapehu. Through age dating of the flanks of the volcano, geochemical fingerprinting of what's in the mounds and those flanks, and looking at the timing of the flanks, compared to the young lavas that fill it in, we can, with Occam's razor, fairly confidently say that this was the shape of the Ruapehu right at the beginning of the Holocene. It finally was, just on the north side, it was temporarily able to build itself a big cone. Then all the ice finally melted away entirely, probably debuttressed it, and it fell off. And it actually has started rebuilding quite a big cone in here. And if you look closely, this is the second cone rebuilding in the scar of the first cone. And this is only 6,000 years old. It's what the Whakapapa ski area is on. It's got a lovely crater in it. For some reason, it's not erupting right now, but it's been erupting a lot a few thousand years ago. All of this really only becomes possible when you integrate all 6 or 7 of those techniques that I've described in the talk so far. So, stepping back globally, this can't be that unusual just at Mount Rainier in New Zealand. We went to British Columbia and had a look up near Whistler, where this had been documented since the 40s and 50s. Again, very similar textures, including those hedgehogs of ice, meltwater tube confined lavas. And actually, with the magma ice community, it's probably pretty common. During the ice ages, at temperate latitudes, there's probably a lot of volcanoes where this is a dominant process at. And it's even in the Cascades, it's really only Rainier that's been reinterpreted this way. But there's a lot of scope to look at other volcanoes at temperate latitudes from this kind of lens. And obviously, it's the right lens for looking at Iceland right now. So that's ultimately the map we produced. It's a nice printed map with a legend and everything, but I've pulled that off so I can show it on a PowerPoint. You can see all those moraines, this extensive glacial outwash, and the oranges and reds are the color-coded ages of volcanoes. And if I zoom into Tongariro, you know, it starts to explain some things. The reason Ngātahoe looks like this beautiful, perfect cone is because it's only in the Holocene, the last 10,000 years, that this valley has been ice-free. And the vent that used to have to fight with ice here doesn't have to anymore, and it's finally been able to build itself a nice, beautiful cone on what is otherwise a very roughly built magma ice fight that is Tongariro, and the same sort of thing for Ruapehu. So I'm going to finish out with the relevance to eruptions and hazards and about whakaari. We spend quite a lot of time working on hazard maps and emergency management. 2012 was the last eruption in Tongariro National Park. There's an ash plume you can see going out to the coast here. It was an overnight eruption. I spend a lot of time building hazard maps as well, collaborating with emergency managers, local Maori, who are tangata whenua, people of the land, and obviously our scientists and other government agencies building long-term background hazard maps. This one describes where most of the hazard is if you were to, on a quiet day, walk across the Tongariro crossing and what might happen. But we also continue to iterate on the way we build hazard maps for events. So this is the hazard map that evolved during the 2012 crisis. It was actually the product of a lot of science from the universities. So this is flow models for the pyroclastic flows, seismicity around where the vent might localize to, and a lot of debate about what the and input from emergency managers on what the restrictive and instructional text on these maps would be. It took about 170 emails for me to work through various iterations of these hazard maps during that crisis. We've got the same things for Ruapehu. The last eruption at Ruapehu was 2007. We worked with emergency management to help them with communication for the ski area and safety around climbers going to the top of the mountain. We helped them work with designers on other aspects of public education around mud flows or laharas in the ski area. So these are drop bars that you pull down over you when you're on the ski lifts. And we partner closely with social scientists. I work a lot with David Johnson, Julia Becker, Sally Potter, and others here, Marianne Thompson, around social science on hazards, especially volcano. This is an example where we run an annual warning test for the Lahara warning system, the mud flow warning system on Ruapehu. And we get observers to count the number of people at risk from mud flows when they start. And then there's a warning system that's triggered on this volcano that when there's an eruption detected, it uses a loudspeaker to tell people to move out of the valleys to get away from these mud flows that could come through the volcano for the ski area within as little as 2 minutes. And what this really highlights is at the end of the exercise each year, the red bar is the number of people who haven't moved to safety. And so Department of Conservation does a lot of work around risk management and communication, but it's really hard to deal with these residual risks. And if you get this close to a vent on an active volcano, there is always some residual risk. And I think that's a key message behind all of this. It's all about risk management. Risk elimination is very difficult. We've started moving to new technologies. This is something Jeff Kilgore is working on. We're now using drones to track skiers, doing particle and motion tracking rather than just having to use observers. And you can ID the individual skiers and watch them move in and out of safe zones. I've pulled the movie out of this because I wasn't sure how well it would work over Zoom. And the last point about interdisciplinary work in Tongariro National Park, we do learning from we do a lot of work around learning from social scientists and from a design and communication background. So these are the maps I showed you before for Ruapehu. Bringing in Danielle Charlton, who's a postdoc in design with us to set up a new national hazard mapping framework, has led to completely different approaches to highlighting important key messages about safety and what to do, and also what the hazards are and the risk to people for both Tongariro and Ruapehu. You can see there's a complete change in the way we draw a map when it's an emergency manager and a scientist trying to guess how to draw it, compared to actually a design academic doing a decent job of it. So I'm going to finish out now by spending a few minutes talking about the Whakaari eruption. So this is, it's moved slightly. This is Sally Potter, Nico, and my presentation just around a few aspects of that Whakaari tragedy. So we'll be talking about the eruption mostly for the next few minutes, but just keeping in mind this is a huge impact for the family members of the 21 people killed on the day, and there's a lot of similar number of people dealing with life-changing burns and injuries from this. So don't want to diminish that, even though we're mostly talking about earth science right now. So Whakaari White Island, as I mentioned at the beginning, is another one of these cone stratovolcanoes. But in this case, only the tip of it is poking out of the ocean. Because it's offshore, the vast majority of it is underwater. And so the crater and just the top of the volcano is the only part accessible and sticking out. It's about 48 kilometers offshore, right here. And it's a popular tourist destination, like many active volcanoes, because you have beautiful hydrothermal vents, hot springs, and fumaroles, because there's a lot of energy in the system from recent eruptions. And we've got many tens of millions of people visiting volcanoes like this all around the world every year. And at Whakaari Tongariro National Park, this is growing by percents or tens of percents each year. And I know the same is true in Japan, for example. Whakaari itself gets about 30,000 visitors a year and growing, or it was growing. We've seen eruptions there before in 2013 through 2016, most recently. And then last year in September, when the lead up to September, we were seeing an increase in tremor, ground vibrations there, which is a classic volcano unrest indicator, and some chemistry changes. And so we released a series of volcanic alert bulletins describing increasing unrest and the possibility that the chance of an eruption was increasing from September through to December. And then on 18th of November, right in the middle of those, we raised our alert level from 1 to 2. So we have a descriptive alert level system in New Zealand that goes from 0 to 5. 1 and 2 are unrest levels, so minor versus moderate to heightened volcanic unrest. And that's the highest we can put it if we're not in an eruption. And then 3, 4, and 5 are minor, moderate, and major eruptions. The detail is in the bulletins that go with that. So on the 9th of December at 2:11 p.m., there was a sudden, within the context of this heightened unrest at level 2, there was a sudden onset, short-lived phreatic, possibly phreatomagmatic eruption, we're not sure, but it produced a surge in an ash cloud, and it was steam-driven, that's the key. So you have this, at these high-energy volcanic systems, where you've got a lot of heat ultimately coming from magma at depth, you've got a hot water system, including a lot of steam, creating those fumaroles and pools, and the steam component can suddenly destabilize and basically explode. It lasted for about 1 to 2 minutes, and it produced flying rocks in a surge, which is a hot ash cloud, a pyroclastic density current of ash, hot water and steam, maybe in the realm of 150 to 200 degrees Celsius, and as I said, some flying rocks. Now, geologically, it may not be the largest event, but it was a hugely impactful event and a massive tragedy, because at this volcano, people come very close to the crater. They're choosing to go to a very close location, partly because it's an island, and so the only place you can get is quite close, and partly because that's where the really interesting things are to see. On day 1, just talking through the way we interact with an eruption. I've talked previously about geological maps and hazard maps. With an eruption, we initially issue a volcanic alert bulletin saying if there's been an eruption. This is for wider emergency management of the public and also for aviation. We raise the alert level to 4 initially. When we've had an eruption, we don't know how big it is often initially, so the default is 4. And then we lowered it to 3 by 4:15 p.m. Once we realized the scale of the eruption. So minor eruption ultimately. But that's a minor eruption in terms of the geological scale, obviously massively impactful in a large tragedy. So up to 4 and then back down to 3. Our toolkit for communication includes making sure we, with our social scientists, think about empathetic messaging, especially when there's been a tragedy. We include alert levels. We included eruption likelihood for the first time in this and following this eruption. We've used this before for our staff life safety, and I'll come back to in a minute. That likelihood was asked for and used by defence and police on their visits to the island in the coming days. We describe the current volcanic activity in bulletins and scientific interpretation and things related to monitoring, sometimes links to other agencies. In the 3 days following the eruption, there was high uncertainty around the eruption potential. So after an eruption, you have a strong chance of a following eruption. And then after about a day, we had increasing tremor. So this was that kind of context of months of lead-in tremor. And then this was the tremor during the eruption. And after a day after the eruption, we had this massive and sustained increase in tremor. And we had high gas concentrations, sulfur dioxide at very high levels on the 12th of December. So on the day after the eruption, we estimated basically an equal likelihood of no, these are offset slightly, sorry, an equal likelihood of no eruption and a smaller or similar sized eruption, and that a larger eruption was least likely following the initial event. And it's difficult to make those types of calls from a monitoring point of view with such high uncertainty. We continued after that to use our expert elicitation procedure to put out daily likelihood assessments, numbers to the public. And that's because the police and defense wanted to use it for basically body recovery decisions on the island. Sorry, someone just slipped something under my door. So we basically calculate that eruption likelihood using an expert elicitation process, where all of our scientists elicit a probability of eruption in a certain time frame, and then we recalculate it out to an hourly risk of loss of life. And we use it for our own safety access distance decisions, basically. And we continued to release that, and we have continued to make that available through into this year following the eruption. And that's a really big change. I think we were already the only observatory that estimated probabilities, and we're certainly now the only observatory releasing those for others to be able to look at. You can see that massive change from before the eruption to after the eruption. Recovery operations of the remaining bodies left on the island occurred on Friday, the 13th of December, and they were informed by that eruption probability work and on-site volcanologists. But again, the real chance was around another steam eruption, and there's a real chance of that just happening suddenly without any precursors on the day, just like the original eruption on the Monday. As well as the probabilities, central government and media really wanted to see the safety distances that our own staff use based on those probabilities. So we had to rapidly work with Danielle at the University of Auckland to produce simplified maps to explain to the media and the public what those probabilities would mean for our own staff in terms of no access or limited access. And so we did a lot of work. I spent quite a bit of time with the Prime Minister's Chief Science Advisor, thinking about who our audience was and how best to communicate some fairly complicated science, but in a clear and concise way. And we had a wide range of other communication channels in this event, and just really recognizing that, with the proliferation of social media and YouTube, our comms team is very busy servicing a wide range, not just conventional media channels after an eruption. I think that's my last slide in my presentation. Let's just say thanks. I'll leave this on the screen. This is a pitch to please visit our GeoTrips website, which is a collaboration with our Geoscience Society. It's got an increasing number and already has many field trips around geology throughout New Zealand. So it's an education resource, but also a tourist visitors resource. So feel free to go to that and let us know if you have any suggestions on how to improve that.